Hi everyone. In this video we're going to do example 4 from antiderivatives. We're getting close to wrap up on this finding antiderivatives analytically. We're also going to look a little bit at some of the applications of antiderivatives in this section and a little bit about trying to sketch graphs of antiderivatives. So before we get there, this one asks you to just use some of your basic shortcuts, and then it starts to get into a little bit of an extension of that. So this deliberately is getting ahead of where I really want us to be, just so that you can see where we're going. So just like before, pause, see if you can crunch your way through some of these. At least a couple of those should be easy. Remember, you can always make a guess, take the derivative, and then try to adjust from there. As we get through here, we're going to get some that are definitely not just basic shortcuts that we know from Calc 1. They're messier shortcuts that we know from Calc 1. So you can kind of try for some recognition there. Can you recognize any of our messier rules in there? The product, quotient, or chain rule. Okay, so hopefully you've already worked through some of these. Please do. Cosine, that's one of the basic ones that we just worked on. So if we want to get cosine, we need to take the derivative of sine and always think carefully about whether or not you need a minus in the mix. Here we do not. The derivative of sine x is cosine x. There could be a plus c involved. We throw that on just to make sure that we're covering all our bases. Part B steps it up just a tiny bit. What if we have a 5 times cosine of x? And the answer is not very much is different. Coefficients just follow through when we take antiderivatives or derivatives. So we're going to have a 5 sine x. Okay, so here's where it actually starts to get a little trickier. This is not just a coefficient of our basic function. This is a basic function of another basic function. So this is composition. Whoa, composition. And composition is tricky. We know that to take, I hope we know, that to take derivatives of a composite function, of a composition, you need the chain rule. So we're going to have to start trying to think our way backwards out of the chain rule. I don't think this one is anything too unreasonable. In fact, maybe even messier ones aren't too unreasonable at this point, but we are going to learn specific tricks for this in a little bit. However, this is great practice to get us going. I can make a guess that I had a sine 5x to start with. I really do want the 5x to be in the sine function, because otherwise when you take the derivative, there's nothing that's going to make that 5 show up. So this is a great starting point. However, if we try and take the derivative of sine is cosine. The chain rule says leave that 5x alone and then add on another piece, another factor. This new factor should be the derivative of that 5x that we left alone. So only touch, when you have composition, only touch one function at a time. We're always working our way from the outside in. In fact, that's not any different than any of our other rules. We're always going from the last step order of operations wise backwards to the first step order of operations wise when we take derivatives. So if you could look at something and say, if I plugged in an x, what steps would I do in what order? You always reverse that order to take the derivative. Okay, so long sidetrack. No wonder my videos get long, right? If we take the derivative of sine 5x plus c and we get 5 times the cosine of 5x, we're really close. We didn't want a 5. So we're going to put a 1/5 out in front, which will cancel our 5, and then that is perfect. So that is a chain rule that we're reversing. But if there's simple enough compositions where it's just a basic function and then the inner function is linear, I think we should be able to guess and check our way out of that for sure right now. Again, I'm asking you to guess your way out of harder things here, but mostly we're going to save that up until we get to the next chapter. So if I'm looking at this x squared cosine x cubed, that's a product, and we don't have a way to reverse a product rule right now, but this is a very specific sort of product. Notice that I'm taking the cosine of x cubed and I'm multiplying by an x squared, and give or take a coefficient, the derivative of x cubed involves an x squared, right? So this is actually looking something like a chain rule as well, as opposed to a product rule. So this was one thing that gets tricky with antiderivatives, is that if you're looking at a product and you're trying to go back to where it came from, you have a couple of possibilities. It could have come from some sort of product rule, or it could have come from some sort of chain rule. So it's not always immediately clear just based on the fact that it's multiplication. So I'm going to say I want a sign in the mix, just like last time. And if I want to end up with a cosine of x cubed, I better start with the sine of x cubed. There's nothing you would do in taking derivatives that would change the input of that function. So if I think about starting to check that, the derivative of sine is cosine. We would leave the x cubed alone. We would then multiply by the derivative of the x cubed, which would give us a 3x squared. And this is actually pretty good. We've got the cosine x cubed, we've got the x squared. My only trouble right now is that I have a 3 that I don't want. And it's a coefficient, which is really easy to fix. So if I throw 1/3 out here, it would cancel out that 3, and I would have exactly what I want. So the antiderivative of x squared times cosine of x cubed is 1/3 sine of x cubed plus c. So I do think this is really good practice, because this can be one of the hardest things. Spotting those things that came from the chain rule is really important. The next one is even messier, but notice this time I do have products. In fact, I have 2 of them, but I don't see that chain rule thing. I see sine x multiplied by 3x squared. There's no composition in that. That's just a basic function multiplied by a totally unrelated basic function. And then the same thing over here. I have a basic function multiplied by a totally unrelated basic function. However, if I look at this first term, second term, so before the plus, after the plus, I do see some connections here. Sine and cosine are related by a derivative, and x cubed and 3x squared are related by a derivative. So this is starting to look like much more like a product rule to me. So I'm looking at a first times the derivative of second plus second times the derivative of first. And it's a little tricky because you could go either way, but this is a really big clue to me. There's no option on who's the derivative of who there. 3x squared is the derivative of x cubed. So this would be like the g prime and the g, or f if you want to call it that, which means that this better be the f and the f prime, right? So we always multiply function by derivative and then other function by other derivative in the product rule. Which means I probably started with x cubed times sine x. The product rule says if you have f times g, then you need an fg prime plus a gf prime. And we can check. We can say, okay, we want the second sine x times the derivative of the first, 3x squared, and then we want the first x cubed times the derivative of the second, derivative of sine is cosine, and then derivative of c is 0. This looks perfect. Again, we're going to learn a trick for reversing the product rule. I promise I'm not going to ask you to do a ton of this guess and check, but I want you to think about it a little bit. Last one here. I hope you had a big hint based on that product rule and are spotting that this looks something like a quotient rule. And actually, in some ways, I think it's easier to spot what's what, because we always put the original denominator squared in the denominator of the quotient rule, which means if this really is a quotient rule, my original denominator is sine x. And then what we should see on top is the bottom times the derivative of the top, and this should be the top times the derivative of the bottom. So that means the top must have been an x cubed plus c, and then a really quick check on that. Okay, so we get the bottom squared, and then the bottom times the derivative of the top minus the top times the derivative of the bottom, which looks really good. Okay, thanks for watching.